Welcome to a new video about LC ladder filter design. This is our example number 4. In this example we will again look at the inverse Chebyshev response, but then for a bandstop filter design. We'll see that in the calculation step by step, how we do that, and also verify these in SPICE simulations. So let's look at our objective. We want to design an inverse Chebyshev response of an LC ladder configuration. That will be then this filter. We will design that shortly. It must be a bandstop filter and also using a 50 ohm double terminated shunt input circuit. That means the following: the RF, which is the source resistor, and the load RL must be 50 ohm each. This is normalized values. These are 1 ohm. The specifications are following. We have a maximum passband ripple of 0.6 dB. The minimum stopband attenuation we want is 25 dB. The lower passband frequency is 1 MHz, upper passband frequency 1.144 MHz. The lower stopband frequency is 1.04 MHz and the upper stopband frequency is 1.1 MHz. So we will use these specifications, also the form of the bandstop filter circuit, to design this filter. So let's look at our solutions. Step 1 is the passband bandwidth and also the center frequency. So let's first see that. The bandwidth is the difference between the upper and the lower, so upper minus the lower passband frequency in the omegas. You substitute the values here given, you get now 288 pi times 10 to the power 3 radians per second. The center frequency is again calculated as before using the geometric mean, so the square root of the omega ph times the omega pl, so just the product, again in radians per seconds. You calculate this and you get now 6.72 mega radians per second. That's step 1. Step 2 is the normalized passband frequency, the capital letter omega p, and the normalized stopband frequency, the capital letter omega s, for a prototype low pass filter. We start with the low pass filter as we discussed previously, and we convert that to the bandstop filter. We did it in the example number 3. We converted then to the bandstop filter. So the base is always the low pass filter. This is the formula for the bandstop filter design. So we get now the bandwidth divided by the difference, but it's actually the same, so we get actually just 1. That's always the case. And then for the omega s is the bandwidth divided by the upper minus the lower for the step band frequencies, and then you get now 2.4. Now the step 3 is the filter order of the prototype low pass filter, which will be also our bandstop filter order. That is first the epsilon p, which is related to Amax, and Amax is 0.6, so we just calculate that, you get now 0.3849. Epsilon s is related to a minimum, and that is in this case 25, and you get now this value. Taking this together again in the formula we have also used for the inverse Chebyshev response, also for the Chebyshev response, you get now the values here, you see that, and then you get now 2.9725. And we need to have an integer value. That means we need to take a third order filter. Step 4 is the bandstop scaling factor, which is the KFBS, and that is in this case set to the difference between the upper and the lower stopband frequency, which is actually just 1.2 pi times 10 to the power 5 radians per second, or approximately 377 kilo radians per second. This is an important parameter we will use later for our component values, and that is then 60 Hertz. There's a difference between these two frequencies. Now let's collect everything we have, and also the Km is here shown. That is the gain scaling factor, because we go from 1 ohm to 50 ohm. That is actually shown here. So if you have a 60 ohm here, for example, then your Km will be 60. Step 5 is the low pass to bandstop transformation. This is the low pass filter we know for a third order inverse Chebyshev low pass filter circuit. This is the configuration. This part, C1, C2, L2, and the C3, and these are just the RS and RL you see here outside. So this green part is actually this. Now we need to transform that to the bandstop filter. But before we move on, let's look at a table of the inverse Chebyshev for the filter order 3. And this is normalized for the stopband frequency of 1 radians per second. You see the components and also the minimum what we require for stepband attenuation. Now we need to have, again, the third order, but also 25. That means actually this row, and these are the coefficients. You see the 1.49178 and also the others. And those are the normalized values of these components. So C1 is 1.49178 farads. That's also for C3. C2 is this much farad and L2 is this much Henry. Okay, now the transformation for the band stop filter goes like this. The C's, all the capacitors will be transformed in a series combination of the inductor and the capacitor. And when you see an inductor, you replace that by a parallel combination of an inductor and a capacitor. That's shown. So you replace that by a subscript P or an S when you make this transformation. So when you now transform this into the band stop filter, you get out this. And you see also the primes for the RS and RL that is actually scaled up to 50 ohm. But let's see that C1 is again this series combination also for the C3 and C2 also. And this L2 is transformed in this format. And you see also in the naming, so sort of coding, that this is now C1. That comes from, this one is coming from C1, is also from C1. This is coming from C2. This is also coming from C2. This is coming from L2 and L2. And this is from C3 and C3. Now we need to calculate these components in total and also check that in the simulations. So let's move towards that. So the calculation of the scaled component values, we need to have the formulas, and this is the first formula, which is actually the component here. You see that, and we also need the KFBS, which is our frequency scaling factor, and omega center, and also the value C1 from the table, which is here 1.49178. That will give us 249 picofarads. Again, the Km is here 50. Now, the inductor is also calculated using this formula. That will give us 88.91 microhenries. Now, the next one is the capacitor for this part, which is actually transformed from the C2. Use the C2 coefficient, use again the KFBS, which is the frequency scaling factor, and also the center frequency. Now you get this 41.97 picofarads. In a similar form for the inductor, this is the value, again using the C2. Now for CS3, use the C3, but it is the exact same as C1, so these are the values. We are exact same, CS1, CSC3. That's also for the inductor the same. Now this part, which is the parallel configuration, that's this formula. You get now 70.78 nanofarads, and for the LSL2, you get 1.245 microfarads. Now for the RS prime and RL prime, they are scaled up, as said before, so you get 50 times 150 ohm, and also 50 ohm for the RL prime. Now we have our components in total. And let's now bring that together here, and those are the values we have collected for our band stop filter. Now the design circuit is then this. You see again, this is the prototype low pass filter, and this is now the scaled up, transformed in the band stop filter in this SPICE simulator. And we will now see that in the actual result in the frequency response that these specifications are met. So let's go now to the simulation results, and this is the body plot for the gain. You see the body plot for the gain only, and you see some values. So let's go one by one. The passband gain is 0.5 because the source and the load are exact same, so you get actually at the passbands, so at the very low frequencies and the very high frequencies, 0.5 as the gain, which is then minus 6.02 dB approximately. So that is verified using these two labels. The lower passband frequency at 1 megahertz is shown here. This is the value in dB, so you go down from the baseline to this value, which is then 0.55 dB approximately, which is less than 0.6, so which is then according to specifications. And for the upper one, which is actually shown here, again a simple for you go down from this baseline at this 1.144 megahertz to this value. Again, this is then 0.56 dB approximately, again less than 0.6 dB as a ripple. The next one is the lower stop band attenuation. That is actually at this frequency, 1.04 dB. In this case, it is this value, which is minus 30.875 dB. From the baseline, you go down by 24.85 dB, which is not that 25 actually, but it is close. So in this case, you see that the design for this case is a little bit off, but for the lower is that. For the upper one, you can see that it is actually sufficient. So it's 25 point approximately 18. So you can say I would like to improve this, then you can go to a higher order, but this is in practical cases sufficient. We also see that we have a couple of notches, notch frequencies here. These are the points where we have the lowest gains. So we can in total say this is good enough for our design, and also we have achieved our goal for this circuit for the inverse Chebyshev response for the LC ladder configuration. Alright guys, if you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.